Okay, let's get started. So, there we go. So, let's get started. We were talking about the web last time. I'm going to finish the couple of slides that we couldn't cover last time. And then for the rest of this class, I'll talk about distributed file systems. Okay. Earlier today, I sent out a note about next week's schedule. Okay, so Monday there is no class because it's Patriots Day. Okay, Tuesday is actually Monday's schedule as far as the university is concerned. So the Monday's class will be held on Tuesday. We'll have another class on Wednesday. Both of those classes are actually guest lectures that we had scheduled a while back. Okay. So one of them is going to be on file systems. The other one is going to be on IoT and smart buildings. Okay. In addition to our two lectures, on Thursday there is a visitor giving a talk that is directly relevant to a lot of the issues that we have been talking about here. It's on performance measurement and scaling performance measurement to Google's applications like Gmail and so on. So I'd encourage you to go attend that talk and try to understand how these issues are relevant in industry and whatnot. Okay, so those three events are two lectures, two guest lectures, and one talk scheduled for next week. The other announcement I want to make is the exam grading is done. We are calculating the statistics and whatnot. I am going to send out a mail with the distribution of scores, and then maybe tomorrow or day after, whenever there are office hours, the TAs will have the exams. You can go pick them up. Okay, I didn't want to wait till next week to hand them out, so you can go pick them up sooner than that. All right. Okay, so let's continue with where we left off last time. So last time I was talking about web proxy caching, if you remember, and we talked about this case of hierarchical proxies caches, where you have caches that are arranged in a hierarchy. They collaborate with one another to serve user requests, and I gave an example animation which said if the proxy has the requested web page, then it's a cache hit, everything is fine. But if it doesn't, then the process of trying to ask all other proxies nearby or up the hierarchy to see if they have the web page can take a long time, and that miss can significantly increase the latency that the browser sees while all these proxies are actually exchanging messages to figure out if there is a page, the page is cached somewhere. Okay, so I'm going to show you a different architecture that will try to avoid this problem, and then we'll take both of these ideas and generalize it to content distribution network, okay, which is really a global collection of proxy caches, not just a small number. Okay. So the question you could ask is, if you want to still have caches collaborate with one another, cooperate with one another to serve user requests, how can we actually ensure performance? Okay. So the assumption, so in this picture here, all these green circles are caches, and they cache some web pages. The user, these white boxes are actually clients or user browsers, and user browsers ask a local cache if there is a web page cache there. Okay. If the web page is cached locally, you're done. There is nothing to do. Okay. You just return that response and you are all set. If you don't have the local cache does not have that web page, it has to fetch it either from the origin server or from a nearby proxy cache. Okay. And we want to make sure that the process of figuring out where, if it's cached anywhere nearby, is fast. Okay. How would we do that? What's one technique we could use to speed that up? Okay. In the previous case, we actually sent a message and asked the proxy saying, do you have this web page? So you would get a yes or no answer depending on whether it's yes or no. If it's a yes, you will ask the web proxy to send it to you. If it's no, you will send it up the hierarchy, and this process will continue, and that takes a while. So how could you speed up this process? Yes?
You can say which cache has which like items.
Okay. So you basically keep a table or a directory that tells you what proxies have cached what content. So not only do you have a list of pages that you have cached in your local cache, you also have a table that tells you what others nearby have cached. Okay? So now all you have to do is whenever there's a user request, you first look in your cache, do you have it? If yes, you're done. If not, you basically look at the table to see who else might have it. And then if you find some other nearby cache has it, you fetch it from there and serve. Okay, so there's no need to ask the proxies because you're keeping a table. Okay, of course, now you have the problem of keeping this table up to date. You have a question there?
Okay, I guess we're about to get into it. I was going to ask if the table is local or if there's a global.
Okay, the question is the table local or global? Every node will now have to have some table. Okay, which means, and the table has to have all the entries of web pages that nearby proxies have cached. It's not every single proxy, but just whatever you think are near to you and you care about. Okay? But having said that, you still have to ensure that whenever a proxy fetches a new page or it deletes a page because of cache consistency reason, that table has to be up to date. Okay, so you have to keep that. Otherwise, if the table is itself out of date, you think a proxy has a web page, but it's already deleted it because the time expired or something like that, then you have an out of date information. Or if the proxy fetched a new page, but you don't know that it has it, then you might go to the server needlessly. Okay, so now you have the problem of ensuring that the tables are up to date. But let me show you how the technique works, and then we will figure out how we deal with some of this. So here you basically send a request for web page A. That's basically a hit. Or not a hit actually. You look in your table, it's a local miss. You look in your table which says A is cached at node X. So then you basically go to node X and fetch the page. Okay? And then you're done. So now maybe here is a request for node B, and here you don't have that web page locally, neither do you have any entry that says anyone actually has it. So in this case, you're just going to go to the server and fetch it. You don't waste a lot of time trying to figure out if someone else has it. So you basically got that page from it. So lookups are local. A cache hit is going to be at most 2 hops. Okay, you will come to your local proxy cache. If it says somebody has it, you will go there. The worst that will happen is that you had some out-of-date table information and you sent a request there and that proxy doesn't have it. In that case, it will have another hop and go to the server. But that's only in the rare case where the information in your table is inconsistent. Okay, if you keep it consistent, that shouldn't even happen. Okay, so either you will get it locally or get it from a node, but in the worst case, you might have 2 hops with 1 extra because you had a wrong hint. Okay? And if you know that no one has it, you just go to the server and fetch it. So that speeds up, allows the caches to collaborate. It speeds up the latency of cache misses significantly. Okay? All right. So now we'll take these ideas. These basically are hierarchical caches. And if you have a global network of these caches, you have what is called a content distribution network. Okay, a CDN or a content distribution network is a service that a CDN provider provides to websites that have a lot of traffic or serve a lot of content. Okay? So this is a caching service. So websites can actually sign up for this service, and then the CDN will cache some of their content. And when a user browser tries to access that web page, some of that content will come from the caches. All of it could also come from the caches. Okay? So you as a website provider don't have to set up caches, neither do users. So there's a third party that's providing this service of caching and content delivery. So they deal with cache consistency, they deal with which content gets replicated at which site and so on and so forth. Okay? There are many such providers. The largest one is called Akamai. It's a company that's actually based in Cambridge that provides a global scale proxy caches, tens or thousands of, maybe hundreds of thousands. I don't know the exact number, but lots and lots of proxy caches deployed all over the globe that provides caching service for the end user. Okay? Now they have to, as I said, deal with propagating notifications when content changes at the server. So this is handled internally by the CDN architecture. Okay? So that's one thing. The other thing is whenever a user tries to make a request, the CDN has to figure out what is the nearest proxy cache, because there are now tens of thousands of caches to choose from. Okay, somehow you have to figure out which proxy cache to send this user to serve their request. Okay? And in the case of Akamai, this is done through DNS. Okay, so essentially, they have a special version of the domain name service. So when a request comes in, that Akamai's DNS will actually figure out where is the user. It will geolocate the user first. Okay, so if you say user is actually accessing this web page from UMass, okay, once it figures it out, then it has knowledge of where its proxy caches are located. So then it will be, if the user is at location X, what is the nearest proxy cache to that user? And then that DNS will dynamically resolve to that proxy cache. So you will go to that proxy cache. If that same request came from some other user, it will resolve to some other cache. So you are essentially using the DNS to dynamically point the user's browser to a web cache that is near to that user, so that the latency to fetch that web page is as low as possible. Okay? So this is called DNS level redirection for CDNs, and I'll show some examples of this as well in the next slide. Okay, so it's an active area of research, and there's a lot of work being done here. Here's a picture actually from the book that shows how this works. Here's your client. Okay, the client essentially first contacts the web server. Okay, in this case, we are assuming that the HTML page is fetched from the web server, but all the large images that are embedded in the page are fetched from the CDN servers because they're larger. So you're offloading your load to the caches. Okay, so you get the base document. So then the document comes embedded with all the images. Now when you try to fetch each of those images, excuse me, so those will actually be pointing to Akamai's caching system, and there you are going to go to that DNS server. The DNS server will figure out where is the client trying to access it from, and then send it to the nearest CDN proxy. Okay, there will be lots of those proxies. You will say go to this one, okay, and then you'll go there and fetch the content from that. Okay, so that's at a very high level how a lot of what we talked about in caching actually is employed in the context of CDNs. Any questions on this? Yes.
These CDNs censor or regulate what's on their network?
Do the CDNs regulate what's on their network? Regulate meaning what you cache, is that your question?
Do they say that there's some content that we're not going to cache, because of the
Okay. So question is, do CDNs decide what to cache and what not to cache? So what is put in the CDN's cache is up to the web server, because the web server is the one that signed up for the CDN service. Okay, and then it's up to the whoever is generating the content and putting it on the web server, saying which of these pages or images or content needs to be served from the cache and which one am I going to serve. You can offload the whole website to the CDN, in which case even that first request actually goes directly to the CDN, not to you. But this has been the general principle that simpler HTML text pages you serve there, the images go from there. Now the thing that the CDNs will not serve are dynamic pages. Okay? Only static content is served from CDN caches. Okay, no cache, web cache will actually serve dynamic content, because dynamic content is generated on the fly after every request using a script. Okay, and then you can customize it by putting the name of the user in the web page and so on and so forth. So dynamic content never cached, doesn't matter whether CDN or any other cache. Static content is cached. But beyond that, the CDNs don't make the decision of what to put in the cache. It's the web servers that are paying the CDN to cache their content. So they get to decide what goes in there. It's just like a cloud where you go and get a server and you get to decide what applications to run. The cloud provider doesn't tell you what you can do on that server. Once you get the server, you can run whatever applications you want. It's the same thing here. Okay. Any other questions? Yes.
Not validate documents in the CDNs with dynamic pages to change once every day.
Okay. Question is, can you not do cache consistency with the CDN? And why not do dynamic pages? So dynamic pages are assumed to change on every request. So that is why we don't cache it. But let's leave the dynamic page aside. You could take any page that changes frequently. Okay, so you can cache those pages in the CDN, and then you'll have to use cache consistency mechanisms of the CDNs to invalidate those pages. So that is done. Okay, CDNs have the ability to cache content that changes, and you can invalidate them and then have the caches get the new content. All of what we talked about, those ideas will apply. Okay, but not for dynamic. But static content also changes. You can update an HTML page. That's a static web page. Okay, so that will be handled. Any other questions here? Okay, so with that, we will switch gears and talk about the next topic, which is going to be on distributed file systems. Okay, so today there will be 2 classes on this. Today I'm going to go through at a high level several different distributed file systems that have been proposed and used. We'll start with the Coda file system, which is used for mobile devices. We'll talk about xFS, log structured file system, Hadoop file system. These are all very brief. I'll talk a little bit about Google file system, GFS, and Amazon S3. Okay, it's a very high level introduction to how these file systems work. Next time we will do a little more deep dive in that guest lecture. I won't do that. The guest lecture will do a little more deep dive and look at one specific one, which is NFS, in a lot more detail. Okay, we'll spend the entire class talking about one. Today's class we are going to do 5 or 6 different ones. So we'll do them briefly. Okay, but let's start with Coda. Okay, so first of all, you should know what a distributed file system is. Essentially, in a distributed file system, we assume that your files are stored on multiple servers, 1 or more, that are separate from the client machines. Okay? Typically, when you have a laptop or maybe your phone or your tablet, all the files are stored locally. Okay? That's called a local file system. That's all the files are stored on local disk. In a distributed file system, these files are stored on a remote machine. Okay? There could be more than one machine, but there's at least one remote machine. And you can access those files from that server as if they were local to you. Okay, so as far as the user is concerned, it shouldn't matter whether the files are local or not. You basically access those files. Okay? Now, you might have used things like Dropbox. Okay? That's essentially that's not really a file system, but it is distributed storage. Okay? You are essentially using storage resources or disk space on a cloud to store your files. Okay? Distributed file systems will do all of that and also give you a file system abstraction on top of that. Okay? So we'll talk about a few different ones. I'm going to start with this one called Coda. This is a research file system that was developed at CMU, Carnegie Mellon University, maybe almost 2-3 decades ago. So old file system, but it has some interesting design aspects to it. Okay, this was a file system that was specifically designed for mobile devices. Okay? It was not, most of the file systems until then were assuming that clients are on a local area network, a wired network like an Ethernet, and they are generally always connected. Okay? But when you go to mobile devices, you have a very different model. Okay? If you think of how maybe you use your laptop, okay? So you carry it with you. Okay? Whenever you use it, you are connected to some Wi-Fi network, say. Okay? But okay, when you move to a different location, you will shut it down. You will go to a different network, okay? And then you will connect to a new Wi-Fi network. Maybe you come to work, you go back to your home, maybe you go to a coffee shop. So it goes from one location to another. While you are traveling, it is disconnected from the network. Okay? You are not connected, and then you reconnect. Okay? And maybe sometimes you may be traveling, you take it on an airplane with you, you are working, but it's not connected to any network. Okay? You are basically just offline at that point. So this is how people use their mobile devices. Okay? They connect to different networks at different times. Sometimes they may be completely disconnected from the network, yet you might be using your device in some shape or form. Okay? Question is, how should you design a file system to address these kinds of use cases? Okay? If you assume that all the data is on a file server somewhere, okay, then if you are completely disconnected from the network, you are not going to have access to any files. If you go on an airplane and you don't have a network and you can't connect your file server, you have no access to files at all. Okay? So the traditional model of let's put all the files on the server and you just connect to it over the network does not work in this case. Okay? So we need a way by which you can continue to work regardless of change in network, whether you are connected or not, and so on. Okay? So one of the main contributions of this file system was that it was disconnection transparent. Okay? Users would see all of their files regardless of whether they are actually connected to the server or are temporarily disconnected. It looks the same. Okay? So if you are disconnected, you simply have a local copy of all your files. There is a big cache, so you cache all of the files. You can continue to make changes, and when you reconnect, things will resynchronize. Okay? Even Dropbox is going to use the same model today. Yeah, basically, if you disconnect, your Dropbox folder is still on the machine. it's a cache. You can continue to make changes. When you reconnect, it will actually resynchronize. Okay, this idea actually originated almost 3 decades ago in this file system, and then many other systems like this that were designed around the same time. Okay. So it's a model for mobile clients who are disconnected often. It uses a file cache to make the disconnection transparent. Okay, so you can be at home, you can be on the road, you can be away from a network connection. It doesn't matter. Okay, so essentially what you are going to have is an aggressive cache, and then you are going to actually learn what the user wants and adapt the cache to keep data that the user wants. Okay. It is not possible to take everything on the file server and cache it on your client. You may not have the disk space to do that. Okay, the file server may be very large. So somehow the machine has to figure out what files the user is interested in and only cache those files. Okay. So maybe you cache your home directory. Maybe you cache a part of your home directory because maybe you have too much data. So sometimes when you are disconnected, you try to access a file, it will actually not be available. So you will see that you are disconnected. But your file system will learn, and next time it might start getting those directories and caching them as well. So for subsequent accesses, you don't see that problem. So it will continuously learn what the files the users are interested in and start caching those subsets. Okay, so it has all of these nice features in it. Okay. Now there is of course all these problems of cache consistency and file consistency that are going to crop up, and we'll see how to deal with that as well. Okay, because you might modify a file, that file might get modified on a server, and you reconnect, you will have a write-write conflict. Okay, so we'll talk about that as well. Okay. Now the other thing I should mention before I go into Coda is some of these ideas have also made their way into how source code control works. Okay. In many source code control system, you actually check out something from a repository, let's say as a Git repository or as an SVN repository. You make local changes and you resynchronize. While you are making local changes, you don't need to be connected to the repository server. You can be disconnected. Okay, so you are going to do periodic resynchronization. Okay, that's also something that this system does, as we will see. Okay. Now, this is going into the architecture of Coda. You will see this picture actually shows you essentially the fact that you can have replication in Coda. Each directory can be replicated on multiple servers. You will see that there are two file servers here that replicate that directory. The fact that it's replicated is actually stored in a database called the volume database, which says where is every volume stored. It could be stored on one server, it could be stored on multiple servers, and so on. And you will have an identifier that tells you what server and what file handle to use. So a user can actually go and connect to a nearby server, just as we did for caches, where users actually go and connect to a nearby cache. So you can replicate your data also widely across multiple servers. Okay. Now here is some issues that can actually crop up as a result of this replication. Because Coda assumes that network can get disconnected at any time. That could be the network between the user and the server, or the network that connects all the servers together. Okay, so in this example, we essentially have 3 servers, S1, S2, S3, and client A and client B that are accessing files on this server. And the assumption that is being made in the picture here is that the server got disconnected here. It got partitioned, which means you sliced it. So this client can still talk to that server. This client can still talk to these other 2 servers, but those 2 partitions cannot talk to one another temporarily. Okay? But the file system continues to run, because in this case the volume is replicated. So this client A can actually access files on the server S1 or S2. Client B can access replicated files on server S3. Okay? When that network rejoins, these servers will resynchronize all the changes. They will keep sending the changes to one another, so they again become consistent. Okay. Same thing will happen if the client disconnects from the servers. Okay. In that case, the client has no access to no servers at all. And then it will rely simply on whatever is cached locally on its disk, and that cache is going to act as a proxy for the real file system. Okay. All the applications will think that they are still connected, they can still see all the files, except that the files are actually a cached copy, not the real copy. Okay, so the system will pretend as if it stays connected, so you can continue to do your work. And when you reconnect, it will again run a resynchronization protocol. Okay. And there's a little bit of detail here of how some of these things work. Okay, so when you write, you are going to essentially do write all, read once. Okay, if you remember when I was talking about quorum based protocols, I said that the easiest way to ensure that you read from only one replica is that every write has to be sent to every machine. Okay, so if you are connected, you send writes to all the machines, so they are all replicas are consistent. Then you just need to read from your local server, and you'll get the most up-to-date version of the file. Okay, so that's one technique that is used in Coda. The other technique is how to handle network partitions. The way you are going to do this is every file is going to have a version vector. Okay, a version vector is an integer that is incremented by a local server every time you modify the file. Upon every write to the file or every save to the file, you will increment the version vector. That will give a new version to that file. Okay, so and every server is going to keep track of not only the local version vector for this file, but also the version vectors that it knows at other replicas. Okay, so if all the replicas are consistent, the version vectors will match. They'll say 333, which means you have version 3. You know that the other two servers also have version 3. Okay. Now, when you are disconnected, only your local version vectors will increment, and other version vectors won't increment, because you can only send that write to whatever servers you can see, not to other servers. Okay. So if this client writes to file foo, the version vectors at S1 and S2 for foo will get incremented, but these two servers know that they are not able to send the write to S3, so they will not increment their knowledge of S3's version vector. Okay. So if the version vector was, let's say, 333, okay, it will basically become 443. That 1 and 2 will increment their version vectors, but they know the write has not gone to the other one, so they'll keep that at 3. Okay? And the same thing will happen at S3. If it let's say goes and updates some file, which let's say was at version vector 2 to 2, it will become 2 to 3. Okay? So when you the network partition goes away, you will resynchronize, and the way you are resynchronize, you will simply compare version vectors. Whenever you see any mismatch, if your version vector is strictly greater than the other server's version vector, you have a new update that it hasn't seen, you just send it over. Okay? So if that machine has 333 and I have 334, I know that I have seen a change, you have not, you just send it over. Okay? The problem comes if the same file was modified in both partitions. That is when you will have a write-write conflict, and that's the example shown here, that the version 1 vector 111 became 2 to 1 in this partition for the file foo, and that same file foo was modified by that client there, and it became 112. Okay? Now, when you compare this, you can see that there is a write-write conflict, because you know that these two servers updated their some write without sending that write to this machine, and this server update made a write without updating these two. So that's going to be a conflict. So you will just flag a conflict. This is the same conflict you will see in a Git repository. If two users change the same line of the same file, there is no merge that can happen, it will just flag a conflict. Okay, and the user has to now decide how to resolve it. The system will just flag it and you figure it out. Okay, so conflicts are handled manually, but they can be found automatically. Yes, question? Yeah, so here is so you have server 1, server 2, and it's disconnected from server 3. Okay, so 3 servers. So they all have 111, which is that they started with a consistent copy of the same file. A user went and saved maybe a new copy of file foo. And that, because these two servers are accessible to the user, that write was seen by these two. So they will increment their local version vector, which was server 1 and 2, so it became 2 to 1. Okay?
There's no expectation of concurrent writes. Like a user cannot write to S1 and S2 and S3 simultaneously.
The question is, can user write to S1, S2, S3 while they are broken? Broken essentially means I'm disconnected from that part of the network. I cannot send messages. Right? So that's what a network partition means. Of course, you want to write to all servers. That was the whole point, because we said all writes are replicated at all servers. That's the normal mode. In a disconnected mode, you can only write to whatever can be reached from your machine. We have assumed that the network is partitioned here. that there was a network fault, so this part of the network and this part of the network cannot talk to one another. Maybe there's a router link that got broken. Okay?
What if there were two changes and like S1 and S2 received only one and S3 received only one? Is that scenario possible?
Okay, so question is, if you update the same file in both partitions, what happens? That's exactly the scenario we are talking about here. So if this another client actually opened the same file foo and wrote to it here, then this version vector is going to become 112. This becomes 2 to 1. That's exactly the example that's given here. So now two clients have opened the same file, made concurrent changes, and those changes have not been seen by the other servers. That's a write-write conflict, okay? Because you are basically making changes simultaneously and you are overwriting one another change. So this will be detected because the version vectors will conflict. Neither version vector is greater than the other one, which simply means that there have been concurrent writes. If only one partition had seen a write, then one vector will be strictly greater than the other vector. Then you just send the changes. That's not a conflict. That just means you did not see the write. This means there is a conflict. So you will just flag it and say manually fix it. That's called manual reconciliation. Same thing you will do if your Git repo gives you a conflict. You will have to fix the problem manually. Okay? Yes, question? What if two users change the file? Are you asking when there is no network partition if two users change the same file? Okay, if there is no network conflict, two users change the same file, that's allowed. Okay, now that the file system won't do anything, you are supposed to be smart enough to coordinate or use a lock. That's not the file, that's not really a conflict from the file system's perspective. Because what will happen is you have two users sending writes. Maybe user 1's writes comes first, then that makes the version vector 222 everywhere. The user 2's write comes next. It will make the version vector 333. That user may have overwritten the previous user's chain. That's okay. But everyone has seen the write. So from a file system's perspective, that's not a problem. From a user's perspective, that should be a problem because you may go and overwrite somebody else's writes. Okay? So that should ideally have not happened if you had put a lock if these are applications that are writing to the same file. Like if you have a database and users are just writing to the database, you should ideally have a lock. Okay? Yes?
So in this scenario, would a version control system be like a special case of a distributed file?
The question is the versions control system a special case of a distributed file system? Version control systems or Git repos or SVN, they essentially just do the write tracking and merging and conflict detection. They don't actually give you a distributed file system view. So they're only doing a very small part of what they distribute, because here you're still seeing file servers and you can store files and so on. Okay, I mean, of course, repositories store content as well, but they are not file systems. That's something you want to keep in mind. Okay, they do versioning, which this file systems do versioning, but they do more than just versioning. Okay, so there are some similarity in concepts, but you have to realize there's a difference between a Git repository and a Windows NT file system. They are doing two different things. Okay, any other questions here? Okay, so here is how the disconnected operation works. So the previous case just showed us how we can handle writes and how the writes get replicated and so on. But what happens when the user simply disconnects from their network and just goes offline? Okay, so basically this state transition diagram is going to show us how each laptop or how each mobile device is going to work. So it will be in one of three states. Okay, it's going to be in a state called holding, emulation, or reintegration. When you are connected to the network, you are going to be in holding state. In holding state, you are simply trying to cache whatever the user might want before you disconnect. So that's called holding. Okay, you're going to create a hoard of files, which is a cache of files that you keep downloading from the server. Okay, and once you disconnect, you are going to go into emulation mode. Okay, now when you're disconnected, you're no longer you can no longer access the server, but your client will emulate the file system as if you are connected. So all the cache files will just look like normal files. Okay, so you can't actually tell that you are disconnected. Only way you can tell is if you try to access a file that somehow your machine was not caching before you disconnected. Then you will get an error because the file is not accessible to you. But if you access files that are in the cache, it will look exactly the same thing. So you can continue to work Your applications will run the same way. You can write files, open files, create new files. All of that will work exactly the same way. Okay? And when you reconnect, you are going to go into reintegration mode. In reintegration mode, you will take all the changes that were made while you were disconnected, push it to the server, and then you will ask the server what were all the changes for my hoarded files that you saw, and you will bring them to your code. Okay? So you will resynchronize two-way. Okay? And in the process of doing that, if you see a write-write conflict, like we saw in the previous case, you will flag that again, saying some user made a change on the file, this user made the change in their cache, they conflict. So fix it. Okay? So you will also do the same thing, which means the cache will also have its own version vector that it will keep track of to see what changed. Okay? So it will essentially look the same as if you are never disconnected from the network. Okay, so you go back after reintegration is completed, you go back to hoarding. So you will basically cycle through the state depending on what state your machine is in at any given time. Okay. So from a user's perspective, this is convenient because users are not explicitly doing any active management of the file. Okay. Users don't have to say, I am going to go travel somewhere, I may not be connected to the network. Let me actually keep a copy of all my work on my laptop before I disconnect. And you don't have to say, now I'm reconnected, I'm going to copy the files back. Normally you will do this manually. Okay, here the system is doing all of that for you automatically. Is that clear? Okay, so that's basically what Coda does. There are some additional details that I'll mention briefly. Okay, and then we'll move on to the next file system. So another nice aspect of Coda is the way it is actually going to track all of the changes, etc., as it gives us transactional semantics. Okay, every set of writes or a single write looks like a transaction. It is tracked. You update your version vector. You will also give serializability guarantee as if this was a database, although it's a file system, not a database. Okay, writes just look like updates to your store. Okay, and then if you give asset property, they have to be serializable, so you can track the order in which this happened and so on for consistency reasons. Okay. Very few file systems actually give you transactional semantics. Most of them don't do anything like that. They just give you simple what are called Unix semantics, where you open a file and you write the changes, they get flushed to disk. There's no notion of transactional semantics and so on. Because here things get disconnected and you want to ensure that no matter what happens, you want to be able to reconcile and find conflicts and so on, they put much stronger semantics. They made it look like every write is like I'm updating a database. Yeah, so it is a little more heavyweight than normal writes, but that's the design choice they made. Yeah, so it's a rare case of a file system that actually gives you transactional guarantees on your writes. Okay, essentially asset property, serializability, and so on. Okay. And then of course there is caching, which I won't go into this long picture, but essentially the way this implements cache consistency while you are connected is through this notion of callbacks. Okay. Essentially server push consistency, not pull based consistency, because you are aggressively using caches. Okay. While you are holding, if some change happens at the server, your cache better know what it is. Okay. So the server is actually keeping state and pushing any changes that it receives if the client is connected. If you're disconnected, you can't be told that the file has changed. But while you remain connected, you are going to get consistency to callbacks. Callback simply means that the server is essentially going to push you an update. The OS is going to notify an application or the cache that the file has changed. Okay? So push-based consistency. Okay? Most other file systems that we'll see actually use pull-based. Very few will use push-based consistency. That's another difference between Coda and some of these other techniques or other file systems. Okay, any questions here? Yes, question.
So is it the case that all the clients and the servers need to be able to manipulate the file of different formats like factory to
Okay, maybe I'm not understanding your question. Are you asking in a distributed file system, should clients be able to access files that have different file formats? Okay. So here we are assuming that the distributed file system is essentially one entity. Okay, meaning it's going to use the same file format across machines. Okay. Now when we come to NFS next time, what we'll see is NFS is not really a distributed file system. It's a layer that sits on top of a local file system. Okay. So NFS layer actually can interoperate with any type of local file system. So it will work with NTFS or ext3 or ext4, whatever your local file system is. NFS is simply a layer that makes those files accessible from the outside. Okay. So in that sense, it is a distributed file system. It's not a pure distributed file system. In this case, there is no such thing as a local file system. All the files are accessible on multiple machines. So that is the entire file system itself. So this interoperability issue doesn't come about here because the file system itself is built natively as a distributed file system. Okay, does that answer your question?
So, like, so not all the, let's say if you have Unix system, all servers are in Unix-based system, operating system, and not like Windows.
Okay, so the question is, what is the operating system? So you have to distinguish between the file system and an operating system. Many different operating systems can have the implementation of a file system. Okay, so Coda can, for example, be a file system that runs on Windows. It can be a file system that runs in Linux. It can be a file system that runs on a different OS. Okay, but regardless of the OS it runs on, it will have its own native format that's independent of whatever local file system that the OS might support. Okay, so that's the, so it will be a distinct file system from the OS's file system. That's the thing to keep in mind. Any other questions on this? Okay. Okay, so we are going to switch gears, talk about a completely different file system called xFS. Okay, so this was a different distributed file system. This one was also a research file system. This came out of UC Berkeley. Okay. Here there was a very different design philosophy. Okay. So that X in xFS is basically a cross that says no server. Okay. So this is a serverless file system. Okay. It's the closest you will find to a peer-to-peer system. Okay. In a peer-to-peer system, there's no notion of a client and a server. Okay. So in an xFS model, there are no file servers and file clients. Every machine can store files. Every machine can access files from other files. So every client or every node in your network can be a server for whatever files are stored on it. It can be a client for whatever files are stored elsewhere. Okay. So you don't make any distinction of there are some nodes that are called file servers and there are other nodes that do other things and so on. Okay. So essentially their goal was, if you basically not have a server, a centralized set of servers, you should be able to scale better. So this is a fully decentralized file system. You are using the storage resources, network bandwidth of all the nodes, all the resources that you have, which means you should be able to scale better. That was their design philosophy. Okay. Now it's going to make the file system look very different than any of the other ones, because clients don't contact a server. Clients have to figure out where the file is stored and then figure out which node to fetch it from and so on and so forth. So it will make many different design decisions that look different. But that's the basic philosophy of xFS. Okay. So it's called a serverless file system because there's no distinguished node that is called a server. So here's a picture that essentially stores several nodes. You'll see that some nodes have a client running on them, some nodes are manager nodes, some will actually have disk space. Depending on what resources are available, you can use the CPU power, you can use the disk resources, you can use both, okay, just to construct your distributed file system. Okay. So with that background, okay, I'm not going to go into a lot of the details of xFS, but I'm going to talk about two important aspects to xFS. xFS combines two important things from storage. One is it basically looks at disk arrays, or it will use basically RAID, software RAIDs. The other thing it's going to use is what are called log structured organization or log structured file system. It combines ideas from these two systems that were developed independently. Okay, so it's going to take RAID and implement a software RAID. Specifically, it will implement a network RAID, as we will see. Okay? And then it will take what are called log structured file system, and it will basically use that log structured file system on top of RAID. Okay? So to understand what xFS does, first we need to understand what is RAID and what is log structured file system. So I'm going to do a brief digression and discuss both of those concepts first, and then we'll see how to put that together. Is that clear? Okay. So first let's talk about RAID. RAID is an acronym that stands for redundant array of independent disks. Okay. So essentially this RAID is essentially a storage abstraction that allows you to take multiple disks, okay, and make them look like one large logical disk. So you can use the storage resource of more than one disk. Okay. So the simplest way to understand this is if you, let's say, don't have one disk on your machine but have two disks. Okay, let's say your laptop has two drives. Okay. Normally you will see two independent drives. Okay, you might see in Windows a C drive and a D drive, or on Linux you might see two different directory structures and so on. Okay. And when you are trying to store files, you'll have to say, should I put it in this directories on this disk or this disk? So you actually see those disks as separate disks. Okay. If you had taken those two disks and made a RAID volume on top of this, you would see one large logical disk that has a storage space that's equal to the sum of the storage spaces of individual disks. You no longer see those disks separately. You just see like a large logical disk that basically looks like it's bigger than each of the individual ones. Okay. This allows you to aggregate the storage of multiple disks. It also allows you to parallelize your requests across multiple disks. Okay. And you don't now no longer have to manage them independently. You just look at it as one large pool of storage, just has more storage space than any individual disk. It's essentially the sum of the storage space. And now once you store any file, it will get internally stored however the volume manager decides to map it to the disk. Okay. So that's why it's called an array of disks. You have an array and then you will make one large logical disk. I'm going to show you an example. Okay. So, but for that I have to draw a picture. So there are several concepts in RAID arrays. Okay. So I'm going to draw a picture here just to show what that means. Okay. So we'll take, let's say, multiple disks. Okay. Let's say take 4 disks. Okay. This is D1, D2, D3, and D4. Okay. Now if you had these disks independently connected to your machine, okay, they are basically going to be seen as 4 distinct disks. Okay. And when you store a file, you say, I want to store it on my C drive or whatever it is, and I'll go to one of the disks. The entire file goes there. Okay. Now in a RAID array, okay, these 4 disks look like one big disk to the user. Okay. They don't look like 4 independent disks. You just see one big disk. The storage space looks like it's a collection of storage space on the individual disk. So when you now store a file on this disk, okay, because you don't say I'm going to store it on one of the disks, you just say I'm going to store it on my array. Okay. The way your file system, the RAID controller will map it is it's going to use a technique called striping. Okay. What striping does is it takes the file, it partitions it into chunks or blocks, and then it stores these blocks on this disk in round robin order. Okay. So block 1 of the file is going to store on disk 1, block 2 is going to be stored on disk 2, block 3 of the file goes here, block 4 goes here, and then you continue. Okay. So you're going to do round robin. So this is called striping. Okay. So files are no longer stored on a single disk. Every file is partitioned into smaller chunks or blocks, and those chunks are distributed across all the disks. Okay. That technique is known as striping. Is that clear, what I just said? Yes, you have a question. Okay, that's a good question. So we'll talk about that. So question is, what happens if a disk fails? Okay, now if you had the previous case where disks were actually visible as independent disks, which in industry this is called just a bunch of disks. Okay, so it's called JBOD. You'll see all these acronyms. Okay, there's RAID and so this basically means I have no array. I just see all my disks. So if you have this organization, okay, you'll store some files here, and so on. So if one disk fails, all the files that were stored on that disks are gone. Okay? But all the files that are stored on the other disks are still accessible to you. So you will lose 1/n of your files if you lose one of the disks. Okay? If you actually make a RAID array, you are going to stripe your files. Every file is stored on all the disks. So now if a disk fails, you are going to lose 1/n of the data of every file. So every file gets impacted, okay, which means that you basically have no data at all. Okay, which is much worse case, but that is why we'll see that's why it's called a redundant array. I have not come to the redundant part of the disk arrays yet. I'm simply saying what happens if you stripe the. Okay, what is striping first of all? Okay, so that's basic. So now you can ask why do you need to do striping at all? Okay, so what did you gain by doing this? Why would you not take a file and put it here, 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 or here, there independently, internal? Why did you want to stripe? Okay, so let's think about that. Let's not worry about failures, we'll come to that. What does striping give you? Yes? There's more than one advantages, so maybe you can each say something, yes.
You can like access them in like multiple threads.
Okay, or something.
This is same parallel access.
Okay, so the first thing you have to realize is you are getting parallelism. If I read this file, I'm going to send 4 requests to 4 disks, I'm going to read it in parallel. So I get speed up. Okay, so this is same as multi-core and so on. Now you have multiple disks, so every file is stored on every disk, I'm going to get parallelism. That's the first thing. Yes.
I think it's also more balanced because if you have like 2 gigabyte file and only 1 gigabyte of disk is available, you won't be able to store it.
Yes. Second advantage, load balancing. Okay. If you had JBOD organization, some files are stored on each of these disks. If some files are popular and other files are not, the popular files will cause those disks to get overloaded, the other disks are underloaded. So you will have load imbalance in your system. Okay, whichever disk has the more popular file will start seeing more requests. Here every file, regardless of how popular it is stored on all the disks. So clearly the popular files will still cause all the disks to get the same number of requests. Okay, so you got parallelism, you got load balancing. Okay, yes.
Maybe duplicate it like just to save like recovering from recovering.
Okay, so we'll come to redundancy next, but let's hold off on redundancy. Okay, this is no non-redundant disk array. So you got parallelism, you got load balancing. You will also not have any fragmentation issues where maybe you put some large files here and there is only a little bit of space left. If you want to store yet another large file on your C drive, you don't have space. I have to move it to the D drive. That's not going to happen here because you're using all the disk space uniformly. Okay, so you won't get fragmentation issues or anything like that. Yes.
Question about, so these disks, are they like disks, I mean, are they like solid state disks?
Okay, are these disks solid state? These disk arrays are not necessarily solid state. You can take any set of disks and you can basically put them into a disk array. You have a hardware thing called an array controller that's basically going to essentially take all these disks and present this logical disk abstraction outside. You can of course use SSDs, but that's very expensive to do. Okay, most RAID arrays are not SSD based, they are just normal disks.
If you had like a disk which you could access in parallel without like in hardware, without you, so over here you should, like the thing that you're getting past is that you can only make one request to a disk, right?
The question is, can you make one request to a disk? That's not true. You can send multiple requests to a disk, the disk will service them in parallel. Every disk can service more than one request. They'll get queued up, it will schedule them and it will service them. Right? So there is no such thing that you are doing sequential access.
But each one is sequential, right?
No. Disks, individual disks are not, the driver can have multiple requests sent off to the disk. The disk will use something like a scan or elevator scheduling to serve them in order. Okay, so but they will reorder, but you can service them in concurrently from the OSS perspective. Okay, so that's not a problem. Okay, but yes, you can only read or write one block at a time. That is still the case. No question.
Am I correct to understand that if this is used in xFS and xFS is decentralized, then each disk is a separate client?
Yes, so we haven't talked about XFS yet, we are still on RAID. But in XFS, each of these disks will be on a different machine. So you are going to do what's called network striping and software RAID. This is called hardware RAID because a hardware controller that's doing this. But you can implement the same thing in software and implicitly you assume those disks are on the same machine, but they don't have to be. In XFS, they will actually sit on different machines. Isn't it the same as BitTorrent? BitTorrent is not a file system. BitTorrent just stores different chunks on different machines and downloads them in parallel, okay, but it's not really a file system per se. Okay, there's a file system that you can run on top of RAID. Okay, but let's talk about the redundancy aspect. So the question that was asked is, okay, now disks will fail, that is true, and the bigger problem is not that the disk failure is going to cause loss of data, but the more disks you have, the probability of failure actually goes up. Okay, so if you take a typical disk, it might have 50,000 hours lifetime. Okay, that's the mean time to failure of a disk, called MTTF. Okay. Now, if you essentially the reliability of n disks, okay, is basically the reliability of one disk divided by n. Okay, because disks can fail independently, so probability that any disk can fail is 1 minus p to the power n. So essentially, as the number of components grows, the mean time to failure drops. So if you have 70 disks, the mean time to failure is down to 700 hours. So every 10, 20 days, you are going to see a disk failure, as opposed to every 2 years or 3 years, you will see a disk failure. So when you have lots of disks in a disk array, the probability that you are going to start seeing failures every so often goes way up. So you have to deal with your failures gracefully, otherwise you are going to get data loss. Okay? And as the array keeps growing, this probability will keep going down. So you will see drop from 6 years to 1 month. So that's for 70 disks. If you have 700 disks, that's going to go down further. Okay? So we cannot just build a disk array stripe and then be happy that we got load balancing and parallelism, because there's going to be high probability of data loss. So how are you going to deal with it? This is where the redundant part of the array comes. We have to use those disks also to store redundant information. Okay? There are many types of redundancy you can use, and depending on how you use redundant data on the arrays, you will get different types of RAID arrays. Okay? They actually are numbered 1 through 5. Actually, they are numbered beyond 5, but the basic ones are RAID 1, RAID 2, RAID 3, RAID 4, and RAID 5. Okay, RAID 0 essentially is this, which means no redundancy. Simple striping, just get one logical disk, no redundancy at all. That's called RAID 0. Okay. RAID 1 is called mirroring. Okay, in mirroring, for every disk in the system, there is a mirror disk, okay, which stores exactly a copy of whatever is stored on the main disk. As a primary disk, there's a secondary disk. Okay. So basically, if you have 4 disks, in this case, there will have to be 2 disks and 2 mirrors. Okay, so essentially, the total capacity of this system will drop to the capacity of 2 disks, because the other 2 disks are simply mirroring what's on the primary disk. So whenever you write to this RAID array, whatever you write to one disk, you're going to write to the mirror as well. Okay? When you read, you have to read from one of the two. You don't have to read from both. It's the same data. Okay? That's called simple mirroring. Okay? So each disk is fully duplicated. Now essentially, if one disk fails, nothing goes wrong, because you still have a copy of that disk on the secondary. So the array controller will transparently start fetching data from the secondary. You won't even know from an application's perspective that the disk has failed. Of course, the OS will be notified, and the OS will tell you that the disk has failed. You better go get a replacement disk and so on. Okay, but the system doesn't stop working. Okay. RAID 2 is similar. Not similar. It has some encoding schemes that I'm going to actually ignore. But now I'm going to talk about RAID 4 and RAID 5. Okay. You will understand now that this is good from a disk failure perspective, but it doubles your storage cost. If you want to have 1 terabyte of RAID array, you have to buy 2 terabytes of disk. Okay. Your cost is essentially doubled, which is a high cost to pay for redundancy. So we are going to try to do something better. Okay. For this, we are going to use what are called encoding schemes that allow you to reconstruct that data on the fly. Okay. There are many forms of encoding schemes, and we'll see that RAID actually uses parity-based encoding. So this is basically at the heart of RAID arrays. So if you have 4 bits of information, D1, D2, D3, D4, or in this case D0, D1, D2, D3, if you do an XOR of those 4 bits, okay, you will get a new bit, which we will call the parity bit. Okay. Now the property of XOR is such that if any of those pieces of information is not available, you can substitute the parity and essentially reconstruct the original. Okay. This comes from a very simple property of XOR, which is as follows. Okay, so if A XOR B is C, okay, the XOR property says that essentially if that is true, then A XOR C is going to give you back B, or C XOR B is going to give you A. Okay, if you have 2 bits A and B, okay, you do an XOR and you get a third bit C, okay, you can use that answer and one of those 2 bits and do an XOR, you get the one that is missing. Okay. So that's essentially the property, and that is, you can essentially do A XOR B XOR C XOR D and then get a parity bit, and then if any of them is missing, you substitute the parity and reconstruct the rest. Very simple. You can actually write your XOR table and verify this. Okay, so that's the property we are going to use. Okay, essentially, rather than XORing bits, we are going to XOR blocks, but it's exactly the same thing. So what we have done here is we basically take block D0, D1, D2, D3, done an XOR of those blocks, we got a parity block. We stored it on a different disk. Okay? So the basic idea is now if this disk goes down and the user says, give me file contents that goes in disk blocks D0, what you are going to do is you are actually going to go read D1, D2, D3, and P, and internally the hardware will do an XOR of them. That will actually give you what was in D's block D0. Okay, so even though the disk is gone, you are reconstructing the contents of that disk on the fly. Okay? In mirroring, there was no reconstruction. You stored an actual copy. Here, you don't have an actual copy of what is on the missing disk, but you can reconstruct it by actually, that is your redundant information that allows you to reconstruct. That is what we are going to use. Is that clear? Okay, so this is actually what is shown here. There's a green disk which is going to store all your parity blocks. Okay, so this D0 to D3 is called a stripe group. Okay, what is meant by stripe group is those blocks are going to be XORed together, and then you are going to get a parity block. So all of those blocks are related to one another, which means if the disk goes down and any block of that stripe group is missing, you just have to get the rest of the stripe group, do an XOR, and you get that block. Okay, so that's the basic property for RAID 4 and RAID 5. The only main difference between the two is in RAID 4, you basically have a dedicated parity disk. Every stripe group will have n-1 block, and the nth block becomes the parity block that goes on the nth disk. So there's a dedicated parity group. Okay? Now this is good from a reconstruction standpoint, but essentially this also causes a load imbalance in your array as far as the parity disk is concerned. Because what happens now is if any block gets updated, if you actually make a change in the file and save it again and some block got changed, you have to read all of that data back. You have to redo the XOR, reconstruct the parity and save it back. So write to any of these files also triggers a write to the parity, because the parity always gets updated even if you change one block in that stripe group. Okay? So what that also means is the write load on the parity disk is the sum of the write load of all of these disks. Okay, because you send one write here, one write somewhere else, one write, one write. So there are 4 writes that will actually get that 4 writes total. Okay, so the parity disk is going to get overloaded. Is that clear? So essentially what RAID 5 does is it basically says let's not actually have a dedicated parity group disk. We are just going to do distributed parity. Okay, we'll basically take n disks. Okay, we'll basically do striping. We'll construct the parity block, but how we store it will actually be interleaved. So in the first stripe group, so when you have blocks 1, 2, 3, 4, the 5th block is the parity. So the parity goes on disk 5. Okay. When you store the next 4 blocks, D4, D5, D6, D7, you will construct the parity, but then you will put it on disk number 4. Okay. Then for the next stripe group, you will store it on disk 3, disk 2, disk 1, and so on. So that's basically spreads. It's the same thing. In your RAID 4, all these 4 blocks are essentially stored here. You just distributed them across all the disks. Okay, that is going to spread the parity load across all the disks. You'll get better load balancing properties. Okay. No better fault tolerance properties, but better load balancing properties. Okay. Now still any disk can fail. So disk is a column here. Any disk fails, then if this disk goes down, if you say give me D8, okay, the array controller will automatically read D9, P, D10, D11, run an XOR, that gets you back your D8 block. Okay, so we'll reconstruct it on the fly. Okay? And the basic idea is eventually after a disk fails, you go and buy a new disk and you put it in the machine, and then the array controller will do a reconstruct. It will actually trigger a internal write to each of the block, read all of those blocks, reconstruct it and write it back. So after a while, when the reconstruction is done, all the contents of the failed disk have magically reappeared. because it's like you restored it from backup, but the backup are the same files with the parity, same blocks with the parity blocks. Okay, so that's essentially what RAID does. So striping, redundancy, parity. Okay, so these are three things you have to remember. From an external user perspective, you don't see any of this. You don't see the parity, that's internal. You don't see the presence of any of this disk. You just see one gigantic logical disk. Okay, it just looks like it is 10 terabytes if each disk is 2 terabytes in size, okay, for an array. So all of that is hidden from the user and the file system. Okay. So every large servers that you will see that needs a lot of storage will internally have a RAID array in it. You don't actually put disks and manage them independently. You actually make a RAID array out of it. Okay, and that's how you will keep lots of data on servers. Okay, so this is basically used in server environment. Typically on laptops, you are not going to see RAID arrays. Okay, so you'll only see them in servers. Yes. Okay, so question is there a performance impact as compared to mirror based? Okay, there is a performance impact. First of all, you have to realize that the extra number of extra storage you need to get has dropped to 1/n from half. Instead of doubling my storage costs, if I have 10 disks, I need to buy that one extra disk. That's all I'm doing. So I have reduced the extra amount of money I have to spend to get handle disk failures. That's the first thing. But what have you given up? Performance will be a little impacted, specifically write performance. Read performance has no problem. You want to read D13, you'll just read D13. That's the same in mirroring or this one. What does matter is the write performance, because if I update D13, that one write, okay, becomes what is called a read, modify, write cycle. Okay. So to write D13, successfully write D13, first I have to read the entire parity group. Okay. I have to then update block D13. I have to recompute my parity, and then I have to write D13 and P back. Those are the two things that change. So a single write has triggered n reads and 2 writes. Okay, because every write has to update the parity. To update the parity, I have to get the entire set of blocks to actually recompute the XOR. So when I write a block, I have to read n blocks, okay, update that one block that I actually modified, redo my XOR and write the modified parity and the modified block. So small writes are very expensive in the system. They trigger D reads and 2 writes. Okay. Large writes, not a problem. If I was writing a gigantic file and update all those blocks, I simply recompute the parity and override them. I don't have to read them first. But small writes which only modify a part of the file will be very expensive in the system. Okay. When you have failures, also it's expensive because you have to do a reconstruct on the fly. Okay, but the benefit is you have less hardware requirement. Yes, your question there.
In the case, in the example that you took, so in that case, why can't we just XOR parity with D13, previous D13 to get D12 XOR D14 XOR instead of reading everything?
So you are asking to reconstruct one of these blocks, you have to get the remaining n minus 1.
For example, if we have to write on D13,
yes.
Then as you said that we have to XOR, get D12, XOR it with D14, XOR
yes.
it with D15.
Yes.
Can't we just XOR it with XOR the previous D13 with parity to get the XOR of all of those?
No, if you just take one block and XOR with parity, you don't get the rest. To get D14, you have to get all the remaining ones in this. You have to take D12, DP, D13, D15, then get D14. So what you are saying does not work. To get any one block, you have to get the other n minus 1 blocks and then do an XOR of them. You don't do XOR of 2 and get something else. That's not how it will work. Right? So you basically see that essentially if that is your parity, to get D2, you have to basically XOR the rest. Okay, so you'll have to read all of them to XOR them. Okay, yes.
So according to this RAID model, by how much are we reducing the number of servers by extra servers?
Question is how many servers are we reducing? You're not reducing any servers, you're only reducing
Extra, the backup servers. Compared to the previous one, when we had for every single.
so these are disks, not servers, first of all. Right? So in mirroring, for every disk you have a backup disk. Okay, so factor of 2 increase. So you need 1 terabyte, you buy 2 terabytes of disk. In this case, for every within every stripe group, if you have 4 disks, you need a 5th disk. If the stripe group was 10 disks long, if you have a 10 disk stripe, you will have a 11th disk. So 1 over n is the increase. Okay, so you can decide how large the stripe group needs to be. So that's what you will do. Read, so question is read throughput impacted? Read throughput will not do any update. Yes, in case of failure to read a block, you have to first reconstruct. If the block is on a failed disk, you have to reconstruct it. If a block is not on a failed disk, you don't have to reconstruct. However, because some reads are going to the failed block, every other disk will see a higher load because it's also helping reconstruction and serving the normal load. Okay, so load will generally go up if there's a failure. Okay, so with that, I'm going to not do this animation. I'm going to talk about xFS, and then we'll talk about log structured organization. Okay, so essentially xFS is going to use software RAID. You have a question? Yes.
Why can't you just use the parity disk and then XOR it with the old version of what you are writing now? That will give you back the n minus 2 objects. And then you have to do 2 XORs instead of doing like say you have D0, D1, D2, D3. And
Yes.
you have parity, which is the XOR of all of them. Okay.
Correct.
Now if you want to write D2, you can take the parity bit and XOR it with the current version of D2. That will give you D0, D1, D3.
Yes.
And then you edit D2. Then you XOR that with whatever you just got previously. And then you just write.
Let me think about that. I think there are some schemes that do that kind of optimization, but it doesn't work if you have failure. Okay, if you are doing writes, you can optimize the writes by doing some. There's still a read, modify, write. You still have to read something. Okay, and you are just optimizing it by not reading the whole stripe group, but at least you have to read the old parity block and the old block. That minimally you have to read. Without that, you can't do anything. Okay, so still there is at least a factor of 3 increase if you optimize it. That's still a high overhead to pay. But let's take that offline. I just want to finish this before the class time ends. So xFS basically is going to take what I talked about was general RAID. Okay, so that is nothing to do with xFS. Those systems can be used in any servers. You can run whatever file system you want on top of that. What xFS does is it takes this concept, it puts these disks on independent servers. Okay, so disks are not inside one machine. These disks are spread across multiple machines, and then you basically take all of those disks that are across multiple machines and provide in using software, you provide this logical disk abstraction. Okay, so this is called software RAID. You are doing network striping. You basically your blocks are striped across multiple machines, not multiple disks within a machine. They are going to be striped across multiple machines. Okay, and then essentially here this is what you are saying. So because reading across a network is more expensive, you will basically have to read the old parity and the data blocks to compute the new parity. So you will do these kinds of optimizations which you may or may not need to do in the previous case. Okay, but small writes are still expensive because you have to run that read, modify, write cycle. Okay, so I'm just going to say one more thing and then we will stop here. Okay, the other aspect I just want to introduce for xFS, which is called log structured organization. Right? Again, log structured organizations are independent of xFS. So they were part of this file system that was developed called log structured file system. Right? The main motivation for log structured file system was this observation that when you have large memory caches in an OS, okay, the disk traffic is going to look very different from if there is no memory cache. And let me explain what that means. Let's say there is a disk that sees 50% reads and 50% writes. Half of the I/O is reads, half of the I/O is writes. Okay. Now let's assume the OS puts a big memory cache to cache frequently read data. Okay. If the cache works well, many of the read requests are going to be satisfied from the cache, and the disk will never see them because you already cached that file and you just read it from the cache. Okay. But every write still has to go back to the disk. You can't just write it in cache, because if the power fails, memory contents are gone. So writes go all the way through the disk. Okay. So the original traffic, which was 50% reads and 50% writes, has now changed to largely being writes, if most of the reads are actually served from the disk. The only read traffic that's going to be seen by the disk are the cache misses. Everything else is actually seen from the service from the cache itself. Okay. So the main observation is in modern file systems, when you have large memory caches, the disk traffic is heavily write dominated, even though the application traffic may be split between reads and writes. Okay. So then you can ask the question, if my file system is largely seeing write requests, seeing rare read requests, because most of the read requests are being served from the cache, then how should I redesign my file system to be write optimized? And general purpose file systems are optimized for both reads and writes, because you assume that you will see equal numbers of them. But now if you have put a cache, my traffic is mostly writes. I see rare reads. So what should I do? Okay, can I now change my file system design or file system layout to essentially be write optimized? Okay. So that's basically what log structured file systems do. What they do is they basically start writing sequentially, and I'll come back to this because we ran out of time, but it's basically a file system that's designed to handle this new scenario that is write optimized generally. Okay. So we'll talk about this not next time, because next class is actually guest lecture. Okay. Once we are done with the 2 guest lectures, we'll resume talking about this. Okay. So let's stop here today. We'll come back to these slides later.